recording. Well, welcome everybody. So this week we're talking about some of the options you have as you're building your data science project in terms of how to analyze your data. And I want to just say to folks, you've got lots of different options. So we're looking at a simple example of, suppose you're really interested in cars, and we are choosing a particular data set that originally was contributed by Cooper Union. It's about 8 years ago. So keep in mind that the data that we're looking at is really from around 2017. But this is something good to point out because it kind of shows you that the models that you build, they don't last forever. You can say, wow, how a lot has changed in the used car market since 2018. I mean, we've seen the expansion of electric vehicles. We've seen changes in pricing in new cars, which has now changed the pricing of used cars. So, one of the challenges in data science is, just keep in mind when you build a model, it probably has an expiration date on it. And that is why these models continually need to be retooled. And that is why there is an area out there that we call machine learning DevOps. So, we're used to the idea that when we build a software application, that there'll be patches and operating system updates and security updates, and that we have to push out these code changes out into production as seamlessly as possible so people can continue to use the systems without them breaking it down. Well, machine learning DevOps is the same idea. It says, if you're Amazon and you have a machine learning algorithm to help with product recommendations, you're pretty much continuously, fine-tuning that. And then you've got to be able to seamlessly, push out the latest machine learning model out into production. So it turns out that not only is there work in developing, training, testing, evaluating these models, but there's actually jobs out there for folks who specialize in the whole seamlessly pushing these out into operations. So machine learning DevOps is a thing. So, one thing I also wanted to mention is they scraped the contents from Edmunds and Twitter. I wanted to kind of give a shout out. This is the Edmunds site. And, one thing you can do is you can kind of play around just to see, well, look how Edmunds, has... you can just see right here, appraise my car. You know that they're using some sort of machine learning algorithm where you put in information about your car and they help tell you, here's its, fair market value. So in terms of picking a problem, it doesn't have to be a real elaborate problem, just simply, I'm curious in how you would appraise this. And then whatever is your favorite this. I'm into houses, I'm into antiques, I'm into, homes. It could be something like that you'd like to build. And then, of course, going out and finding your data. Now, it would be very interesting. I don't know if Edmunds, some sites do put some data sets out there. Of course, you don't necessarily need to do web scraping. Let me put it this way. When you're looking for car data sets, certainly search around and just do, car price, data sets. You can go ahead and, check to see what's out there, you know. Now, the other thing I just want to reassure people, okay. The other thing I want to reassure people, for this class, do you have to be using the most up-to-date information that is potentially available? And the answer is no, because there's a lot of work in collecting the data set. So I don't have a problem at all. If you find a really great data set and it's 2020 or it's 2018, but it's going to give you an opportunity to practice exploring the data, researching this area, giving you a chance to try out different prediction models, trying to look for patterns and associations. It is fine. You can, when you do your report, you can just give it a title, estimating cars value, circa 2018. And when you do the write-up of the data set, you can just mention, the data set was collected and, it was current as of 2018, and it has these values, and this is how it was obtained, and this is what I know about the data attributes. And, when you write up your conclusions, you could just say, I learned a lot, in terms of these skills and working with the data set, and, future improvements would be to, get a more a current data set and to see what has changed when it comes to, appraising the value of a car. So I just want to reiterate that, because I just want to encourage folks that it is okay to pick a topic that you feel very comfortable with, that you feel you can get familiar with, and it's okay if the data's, somewhat dated. Okay. The key thing is that you can demonstrate that you can work with the data. And by the way, again, when it comes to the choice of tools, it is fine. In fact, you're not restricted to using one tool. I've had students start off and they've done some of their analysis in Excel. And they've been able, they say, here are the insights that I've gotten, working in Excel. I then have had students, switch over. And let's go to back to last week. Just see here. I've had students who then have said, well, I remember from, let's see, is it in the Stat 1 review? I've had students who then said, oh, what I was able to do is maybe I got a free version of SPSS. Or I may have had students who said, well, I was able to get, some Power BI, and I was able to do some visualizations in Power BI. I have even, so it's okay if you want to use a package, okay? I've had students, for example, download a package like Weka that allows them to do a bunch of machine learning tasks. So it is okay. It is fine to use starting off with spreadsheets to explore the data. And then if you want to try a package, one of the nice things about being a student and having that ualr.edu, it qualifies you for a lot of free downloads, and you're welcome to check that out. And then the other thing that you are welcome to check out is, of course, is to experiment with Python. I'll also give a few nods to R. R has a very nice, it's kind of like an R package that is a graphical user interface, so it's all point and click, called R Commander. a lot of folks who are want to use R, but they're not real comfortable with R programming can do a lot using the library R commander, because it basically gives them a nice user interface that allows them to point and click their way to getting it to produce statistics and visualizations and build models. And I was going to say, many of the Kaggle challenges do come with folks who have, posted their notebooks. And it is fine, to try to get ideas from other notebooks. The main thing that we tell students is just make sure that you've taken the time to understand what the code is doing for you. And in fact, one of the reasons I have for sharing my code is I figure it's like a recipe book. What you're doing is, build yourself your notebooks. And of course, the things that go into your notebooks are, for examples of, how do you import certain libraries. You may want to say, well, I want to have some notebooks that show me different ways that I can import my data files. Let me put it this way. You don't have to just upload a file from a PC. You can import your data, from your Google Drive or, from some other source. And it's fairly easy to, Google around to see what are your different options for reading in a file. We also mentioned that there's a lot of work that goes into checking and cleaning up your file. And certainly, if you're talking a small data set, you can easily clean up on a spreadsheet. But when you start getting into files that have thousands and thousands of records, it's really hard to spot a missing value or a weird outlier or a strange value. And that is why when you get to these larger data sets, trying to, for example, use code to see, well, are there any weird things that came in as a data type? Do I want to work with all my fields, or are there certain attributes I want to drop? As I say, I think in this example, actually, I think I would have kept a number of these attributes for building my model. But again, this is mainly just, well, here's the recipe. If you want to drop some attributes, here's the recipe for how you do it. Same thing, if you want to rename some columns so they're easier for you to type in, again, here's the recipe, for how you rename some columns. If you want to get rid of some duplicates, here's the recipe for how you can identify duplicate rows and how you can remove them from your data frame. Okay. What about attributes that have null values? Again, here's the recipe. And it is okay, I was going to say, to go ahead, put in some comments. Here is the instruction for checking for attributes with null values. Okay. I was going to say, I have another, if you go to our lesson plan for today or this week, here we go. I've got an even more extensive tutorial on data cleaning techniques in Python. So I was going to say, we just touched on a few things that you might want to clean up. Duplicates, outliers, missing data. But, there may be other things. For example, if you have text data, maybe you need to make sure it's all lowercase or all uppercase. Or, maybe you've got to standardize those text values so they're more consistent. So this is another guide. And again, think of it as just more recipes. And so one thing you may want to do is build yourself some different notebooks. You may have a notebook with all your data cleaning techniques. You may have a notebook for all your visualization techniques. You may have a notebook for your machine learning, different types of ways to make predictions. You may have a notebook for doing text mining. And it's no different than having cookbooks. I have, one recipe book for desserts, and I have another one for appetizers, and, so the idea here is build what you need. Okay. So what we talked about is, yes, there are a number of techniques that you can use to start just going through your data and cleaning it up, getting the values in the way you want them to display, getting the column names the way you want them to display. And you do all that work, and now you're ready to start analyzing. And we mentioned again, here's the recipe. We'll just say, here's the example of doing a simple box plot. Good for spotting outliers. There we go. And so we had a couple examples. We could see price has quite a few outliers. Not so much for cylinders and horsepower. I added this. This is a new recipe. I should add this in. You can do a comparison box plot, and this one is price versus transmission type. Okay. So often. Go. Very good. All right. Yeah, I think that's all. Let me just double check. Yeah, that's all looking good. Yay. Let me just see something here. I just wanted to make it a little bigger. Let me just see something here. I'm just checking one thing off. Okay. It's just okay. All right. It's what I was kind of playing with is the fact that on different screen sizes, your charts might look a little different. So, but anyway, this is a comparison box plot. It is very useful in the sense that what if you want to compare price of the vehicles and you want to know, hey, is there a difference with transmission category? And so transmission category is not a numeric category. There are a couple different transmission categories in this data set. Manual, automatic, automated manual, which I don't quite know what that is, unknown, and direct drive. And here, let me see if I can make this bigger. Okay. So I'll show you what I'm trying to illustrate. Probably went in too much. Okay. But one thing that you can do is try to compare, how do the prices compare, manual versus automatic versus automated manual. And when I look at the median, as I say, it looked better in my office. But one of the things that, I was kind of noticing is that it seemed like something that was automatic seemed to be having a somewhat higher price than the manual or, the unknown, or maybe even, I don't even know what this direct drive is. But this is often when you're looking for correlations between a numeric variable like price and certain categories. Like you might even say, oh, maybe I'd like to see, is there a difference in price between 2 doors and 4 doors? How could I compare that? I just wanted to just mention, when you do a box plot, you can have this box plot say, yeah, look at price, but break it down by the transmission type. And then you can compare different box plots. We were talking at the very end of the period that, one of the things we noticed about price is that there was some outliers. And we mentioned, one technique, there's actually several techniques for getting rid of outliers. But a popular technique for getting rid of outliers is to use the interquartile range, which is the middle 50%, the distance in price between the 75th quartile and the 25th quartile. And there's a general rule of thumb that anything that is 1.5 times the interquartile range, bigger than the 75th quartile or smaller than the 25th quartile, could be considered an extreme value. And we mentioned at the end of the last period, that is because that interquartile range and that measurement, 1.5 above the third quartile and 1.5 times the interquartile range below the first quartile, that's a good approximation for the strongest part of the empirical rule that says basically 99% of your data should be falling within plus or minus 3 standard deviations of the center of your data. And notice here, this is the command that we use to actually say, hey, guess what? For our data frame, we only want to keep values that are less than the upper bound and greater than the lower bound. That is, we want to keep data that is basically not an outlier. And we mentioned that the reason there's a preference for using that interquartile range versus trying to do the same thing using things like the mean and standard deviation is mean and standard deviation are heavily influenced by outliers. So the interquartile range is a little, it's a more robust measure of where the center of your data is when there are outliers present, and what the spread of your data should be, in the presence of outliers. Okay, so that was a good recipe. But again, if you go look at other cleansing methods, you can explore, other recipes for eliminating outliers. And in fact, you could apply this recipe to say, hey, well, let me check, what about, should I be concerned about outliers with cylinders? Should I be concerned about outliers, in my other numeric attributes? Hey, this is where you can, as I say, this is where the work comes in, is just looking at the behaviors of all the attributes and trying to figure out, what seems to be acceptable and which seem to be extreme, and could some of those extreme things represent, things that are not like what I'm trying to model. So for example, if your goal is to appraise the typical vehicle, yeah, you want to kind of say, what's my definition of a typical vehicle? And is a $250,000 Lamborghini, does that fall within my typical vehicles? Or is a 1932 Duesenberg, prized antique car, does that fall within my typical vehicle? So a lot of times you really have to look at the data, ask questions about your data, and think about what is it that I'm really trying to model here. Yeah, Damien says not in my price range. Yeah. What are some other nice recipes? Well, one nice recipe is trying to do some bar charts. So this is one, this is kind of interesting. What this does is it says it's using the make attribute, which is essentially the manufacturer, and it's saying take a look at the value for the manufacturers and actually count up the frequency, the number of times a particular maker appears. And then this is kind of nice. It says, this says, show me the largest 40 makers. And so this is a nice visualization because it's a bar chart, and you can see that Chevrolet is the most popular manufacturer, at least in this particular data set, followed by Ford, Toyota, Volkswagen, Nissan, Dodge, GMC, and then we've got Honda, Mazda, Suzuki, Infiniti. And then you can see as we go out to the end, yeah, we're starting to see some of the more, I want to say, specialty or luxury car manufacturers. And this is where you can set a title, a label for both the y-axis and the x-axis. So this is an example of how to do a bar chart. And as I say, this is a nice way of, again, when you're looking at counting working with your categories, just how many cars do I have in my qualitative variables that represent categories. Okay. Another thing that I wanted to add, I just added this to my notes, is what about a histogram? So a histogram is a special type of bar chart. It's a bar chart that has been designed for numeric variables. So a regular bar chart counts the number of items that fall in a particular category for a qualitative variable. But if you have a quantitative variable, that means the values are all numeric. So it's very easy. You can just say, hey, I would like to plot this is using my PLT library, which is my matplotlib. So we're using a function of matplotlib, and we're plotting a histogram. And by the way, I'm going to pause. You'll notice Google Colab has added a lot of features now. One thing is if you hold your mouse, it will actually just bring up all the different attributes that you could be specifying. Google Colab has also started to add a number of AI features. I was playing around with a notebook that I want to show you next week, and I was amazed. It was, making suggestions for what I might want to analyze next. Their AI engine, when I had an error, it was asking me if it wanted Google Colab to suggest the fix. And a couple times I used it, I was pretty impressed. It actually corrected my code, and I thought, wow, what a time saver. Would have taken me a while to research and make the fixes. But this is where I'm specifying the edge color, the color of the bars. And this is with a histogram. What you do is you say, okay, take this numeric variable and organize it into, we call it bins or buckets. Basically, it says, take that range of prices from smallest to largest and divide it into 30 ranges, and then count up the number of vehicles that fall into a particular numeric range. And so here's the basic histogram. And so this is price, and if you count it up, we have 30 bars. And for example, this bar here says this is essentially telling me the number of cars. The frequency refers to the count, the number of cars. So almost 800 cars, fell into this particular price range, which is looks like in the upper 20s, lower 30,000s. If we were to expand out this chart, we could get a finer breakdown of what these what is the exact range for each of these buckets. Now this was quite fascinating because you'll notice that the histogram looks, in terms of a mound-shaped distribution, it looks pretty good for price. Notice we got rid of a lot of the outliers, so we have a little bit of a tail, but not as an extreme a tail as we had before. So it looks pretty good, looks pretty mound-shaped, does have a little bit of an upper tail. But notice here, this is kind of interesting. I got very curious about this particular spike here. And I went to the original Excel file, and I went to price. And I just did a data sort, and I'll sort by that price. So this is really fascinating. If you take a look at what are the cars that are essentially around $2,000, I mean, we can kind of look at the vehicle style and stuff, but the key that caught my eye was the year, okay? So if we go down through the data set, yeah, let's go down through the data set here. There we go. Yeah, so notice kind of what's all these cars that were all, about 30 years old. They're all priced at about $2,000. And that's kind of interesting. One of the things I was trying to figure out, and this is something that, if you were given this data set, yeah, David is saying this is, so why are all these guys, regardless of almost all their features, $2,000? And it made me wonder, is that basically like a salvage price? Are these kind of cars that, the base price just in terms of salvage and parts is $2,000? Or is this $2,000 just, I don't know. The reason I'm pausing is when I worked at IBM, we had files where they had a person's birthday. And if they didn't know the person's birth date, they would always stick in January 1st, 1900. Not because that was their actual birth date, but that was sort of the default value. If you didn't know their birth date, you put in January 1st, 1900. I was sort of curious, does this mean they don't really have a value and the 2000 is just sort of, well, that's the default value? Yes. Damien was saying if you put 0 in Excel and say, well, if that was a date, what would it be? Yeah, it's January 1st, 1900. So this is uh, so you'll notice that it seems like for a lot of the older cars, it's around $2,000, and that shows you what's so interesting about data science. It's not just we'll get the data and we'll work with the data. There's a lot that goes into trying to understand because that data is meant to be a reflection of real life. And so the question is, in a real life, when you have these older cars, and again, they're all, I'm seeing the same, what I'm seeing is they're all these older vehicles. And notice when you start getting into the 2000s, the price starts to pick up a little bit more. So here we have the lower 2000s, but you do notice that these are still your older cars. So that is something that, certainly you would want to go back to the people who prepared this data set. And if you could talk to them, you would want to ask them, so what's the story with these older cars? Are these an actual value? Or is this just a default value? And another thing that we would want to think about, particularly when you look at that histogram, is are we modeling one population here, or in fact, do we have two populations? Do we have a population for regular, newer used cars, and then do we have another population of junker used cars? And this is another good lesson, when you're looking at your data. It may be that in order to really appraise a vehicle, you need a couple different models. There's nothing that says this is like Lord of the Rings, one ring to rule them all. You may not have one machine learning model that rules them all. It may be that, part of your first job is to kind of ascertain, okay, which population does this vehicle belong to? Does it belong to a high-end luxury market? Well, we may have a different appraisal model for that versus it's an antique car versus it's a typical used car, but it falls into the junker category versus typical used car that represents things within the last 10 years. So these are the things that as you're trying to do your modeling, don't feel like I've got to come up with one model that handles all my data. Your data may represent multiple populations, and it may be that your better strategy is to work with each population to come up with the best model, and then in terms of your appraisal function, you would want to first ask some questions that would help you classify, hey, this vehicle belongs in this category, and for this category of vehicles, this is the best model for ascertaining its appraised value. By the way, another indication here, let me make this a little smaller. Oh, wait a second, I'm pointing to the wrong screen. Probably explain things. Okay. Yes. Another thing is this right here is a nice recipe. This is a recipe for a scatter plot. And again, it's using Matplotlib, and it's using doing a scatter plot where we're looking at horsepower versus price. And so here we have the horsepower, and then we have versus price. And it's kind of interesting. You'll notice here we have this main relationship, and then you'll notice we have these points down here are all those older cars. the ones that were only around $2,000, those are your 1990s, early 2000 models. So it's interesting. Again, it almost looks, when you see that separation, it makes you wonder, do I actually have two subgroups here? This is why, people do cluster analysis. They're actually trying to see, hey, are there some very clearly defined clusters here? This is a nice recipe here. This right here, I'll make a note. This is the recipe for doing a heat map on your correlations. And correlations, this is using, the default is essentially what's called a Pearson's correlation. This is the correlation between numeric variables. Okay. And one of the things I noticed in the code, and again, let me make this screen a little bigger, yeah, so you can really see the code, is what I'm really saying is again, DF is just short for our data frame. That's our array of values that we're looking at. And one of the things that I found now is when you use a data frame and you want to get the correlation function, it used to be that you could just say data frame dot correlation, and it would just look at the numeric variables, ignore anything that wasn't numeric, and put together your correlation matrix. That was last year. This year, it's more particular. It really wants you to spell out, hey, here are my numeric variables: year, horsepower, cylinders, miles per gallon highway, miles per gallon city, price. So it makes you spell out, here's my list of numeric variables that I would like to get a correlation matrix. And then, in order to better visualize the correlations, this is the command for doing a heat map. Okay. All right. And notice here, I actually print out both. I have it print out the heat map and your correlations. But a correlation is essentially a measure of how well two numeric variables align with each other. Correlation has kind of a, I was going to say, we could look at this numerically, but I love I love pictures. Okay. All right. When they're nice and big. Okay. So this is the idea. If you have two numeric variables, Pearson's looks at the linear correlation. So if you have two variables that are, as one variable gets bigger, the other variable gets bigger as well, the closer it is to being a perfect, one for one, change in X for change in Y, the closer it is to a positive one. Negative correlation says as one variable gets bigger, the other one gets smaller. And again, if that was a perfect linear relationship, it would be a -1. And then no correlation means that a change in one variable doesn't seem to have any pattern in the change in the other variable. Okay, so that's how you interpret correlation. Correlation, this is another good picture. Open in new tab. Okay, this is another one. Yeah. Okay. And notice correlation really ranges from -1, which says you have perfect negative correlation, to +1, and you can have Generally, moderate correlation is maybe around 0.5, or on the negative side, it would be a minus 0.5. And then usually weak correlation, anything that's, between a negative 0.25 or a positive 0.25 is considered, just weak correlation. But correlation, as they say, is based on a linear relationship. One thing to watch out for is, let me just, one thing to watch out for is just remember the normal correlation is based on a linear relationship. If you could have a relationship that is nonlinear, and then the Pearson's correlation isn't so great because, for example, if you try to do a correlation on this quadratic relationship, you'll actually come back with a correlation of 0 because the positive, basically this side, which looks like a pretty good positive linear relationship, gets canceled out by this side, which looks like a really good negative linear relationship. And so just keep in mind, this is why often we like to visualize, we like to do these scatter plots or trend lines to be able to check to see, when we go to model this relationship, maybe we need to incorporate a squared term to capture the quadratic, or we might need to incorporate a cube term to capture a cubic relationship, or maybe we need to use a logarithmic or exponential mathematical function in order to capture the relationship between x and y. And so sometimes that's why you may hear people talking about transformations, saying, oh yes, I did have a relationship between x and y, but it was a logarithmic relationship, so I had to do a transformation so that basically I could, in terms of a linear regression, get that logarithmic relationship to look like a straight line. And you can do that, through various transformations. The other place to watch out for is, oh yeah. Yeah, here's another place where you want to watch out for correlations. So so if you just did a straight correlation, you'd say, oh, there's really, I don't see any relationship in the points. But if you add the fact that you have a black population and a red population, you can kind of see, oh, wait a second, the red population is clearly on one side of the graph, and the black population has a different center. And again, that might be an indication when you build your regression model that you need some sort of indicator. Am I talking about the red population or the black population? Because if it's a red population, I'm going to, want to use this linear relationship. And if it's a black population, I want to use a different, linear prediction. And that is why, let's just see. I got too many tabs open, so of course I'm getting, yeah. All right, we'll just go back into, we can just go back into Blackboard, make sure I haven't There we go. So that is why, just exploring regression, it is a very rich area. And in fact, I even included some additional tutorials. A Python tutorial for doing linear regression, which is a wonderful overview of what is linear regression. I also have something more on Python for regression, and I've got some additional things on, certain assumptions, how to use the stats model, which is very useful, how to interpret, and certainly if you go to the prior week's material, you can spend a whole lot of time. I think it's under predictive analytics. Yeah, I've got a whole, again, just more on regression analysis. Regression analysis works very well when you've got some pretty clear patterns between the variable that you want to do the explaining with, the x variables, and this y variable, for example, price, that you want to be able to predict. So regression and the various types of regression, for example, you can use logistic regression for classifying things, is very popular. One thing that will happen is, though, as the associations or relationships between your variables become more subtle or become more complex, that is why we often then move to decision trees and neural networks and other types of machine learning that is able to handle much more complex or subtle interactions between multiple variables on the variable like price that we want to predict. And then you get into things like deep learning and going a step further. And that is for, there are times when we want to classify things. And a great example is, for example, images. And when you say what's the difference between a cat and a dog, this is kind of a neat picture, because we can see, well, the ears are somewhat similar, and the colors, and the face, and it's kind of amazing. The human mind can immediately look at that picture, and we've been trained as to what's more dog-like and what's more cat-like. But if you're trying to train a computer, this is where you get into, people are starting to use different types of more sophisticated neural nets, just because our brains are looking at 1,000 different things: the shape of the eyes, the ears, the size, the color. I mean, our brain is processing 1,000 bits of information and coming up with a decision. Well, I think this is the thing that looks more cat-like to me. This is the thing that makes more dog-like. But that's why as patterns get more subtle and more complex, that's why we have to go even more sophisticated than a decision tree, or more sophisticated than a standard neural network algorithm. Okay. But going back to this correlation matrix, the thing that we're really interested in is price. And we can see that the variables that have the strongest correlation with price is, you'll notice here, a year has a very strong, about 0.65. Horsepower, we see that horsepower has a good correlation with price. And we see that cylinders have a 0.32 that has some correlation, Not as strong though as year and horsepower. The other thing that you can do with the correlation is typically when you're building your models, you want your models to be as powerful as possible, but you also want them to be as simple and straightforward as possible. So if you have two variables that are essentially measuring the same thing, often you may want to play around. Do I really need both variables, or will just one of them be the same? And I'll point some examples out. Check out miles per gallon between the city and the highway. Okay. Notice that one there's a 0.83 correlation. That means that if a car has high miles per gallon in the city, it has pretty high miles per gallon on the highway. This is an example of when you build your model, you may want to play around. Do I really need both city and highway, or should I just have should I just keep miles per gallon? And of course, maybe neither one has the most impact on price, because I noticed both miles per gallon, highway and city, basically had slightly negative correlations. But who else had a pretty high correlation? Now, this is kind of interesting. Oh, cylinders and horsepower. And that one is kind of, I was going to say, you might say, well, when are two X variables, two explanatory variables, too similar? There are different rules of thumb. Usually, let me put it this way. Usually if the correlation starts getting above 0.7, they get into the strong area, you start to get concerned. So it's kind of interesting. Cylinders and horsepower, strong correlation. Is it as strong as miles per gallon, highway and city? No. Sometimes you have to play around just to see, hey, are two things so similar that it's basically, it's like having two of the same X variables. And it can often improve your model by saying, well, look, these two X variables are both measuring the same, if you will, concept or the same type of attribute. I can use one or the other. I can't, it doesn't pay to use both, and I can play around to see which one does the better job of predicting. But the heat map tells the same story, but the heat map uses some color, little extra visualization. So you'll notice in this color scheme, the darker the green, the higher the correlation. The ones you see simply say that, price is perfectly correlated with price, every attribute is perfectly correlated with itself. Okay. And on the negative side, they use a different color. Okay. One more thing that I wanted to add is this. How do you do a regression model? I figured I got to at least give you a recipe for that. And I really love stats model. So that is one thing that I added to this tutorial is I said I'm going to add stats model because what I love about stats model is it gives you a lot of nice, what you do with stats model is you have to say, I want a model that's going to predict price. So you basically say my Y variable is the price attribute in my DF data frame. And then you pick your X variables, and you can Here it might say my X variables, my list of variables that I want to use to try to predict price. I'm going to choose horsepower, year, and cylinders. You can do all kinds of things with regression. You can create, for example, squared terms if you're trying to model a quadratic relationship. You can create dummy variables if you're trying to incorporate, well, this vehicle has a 2-door versus this vehicle has a 4-door. You can incorporate some transformations. Regression is very rich, but what I did here is just illustrate, a simple, 3 numeric variables. And the other thing is typically in most regression models, you want to add a constant value, which is basically if all my variables are 0, what would be my estimate for price? So it's kind of gives it a base reference. And then this is just saying, give me my estimated model between my X variables and my Y variables using, ordinary least squares, and just go ahead, fit the model, and then produce for me a summary. Okay. And so actually, there's so much here that I ended up, I was going to say, there is so much here that I ended up just giving you some links on just how to interpret all of this output. I mean, honestly, we could take a week and just do that. But I can just point out what are the most important things in this model. Well, one thing that I always like to take a look at is this R squared. R squared gives you an idea of how much variation in price is being accounted for by your choice of explanatory variables. So this is saying that roughly about 71% of the variation in price is being handled by horsepower, the year, and the cylinders. The other thing is, a lot of times the question is, hey, so what is the model what is the predictive model? And that falls under your coefficients. And one of the things that I check for is this p-value. P-values close to 0 mean that all these attributes are contributing some value in helping to predict price. So anytime you see a p-value close to 0, that's essentially saying that variable is pulling its weight in the model. It is useful. It is significant in helping you explain price. Okay. And and I was going to say for the model as a whole, it's saying, hey, yeah, this is a statistically significant model. Again, meaning the model as the whole is doing a better job than random chance in predicting price. Now, keep in mind that there's a difference between being statistically significant and actually useful in practice. It could very well be that still, if you're explaining a little over 71% of the variation, that there's still too much variation to be useful. So, for example, there should be something here, number of observations, residuals, yeah, not robust, okay. I was going to say, one of the things that you can often calculate. You can also, for example, get stats models to print out the mean squared error. which is in essence, it's a measure of how much variation there is between your prediction and the actual values. And so I'll give you an example of, you might have a model and it's statistically significant, but it may be that it is still not good enough for making a useful prediction. So if you bring me a used car and I say, well, the value of that used car is $20,000 plus or minus 20,000. That's basically telling the person, well, my model is estimating a predicted price of 20,000, but I could be off as much as 20,000 in either direction, meaning, my spread is your car is worth between $0 and $40,000. And someone was going to look at you and say, that's not really useful to me. Can you give me an estimate where you're confident that your price is within, let's say, $3,000 of what I can reasonably expect to get for this vehicle? So sometimes, as I say, you can have a model, yes, it's statistically significant, but there's still so much variation not accounted for that your prediction range is still too wide. And as I say, that comes from something called you could actually ask stats models to print out what's called the mean squared error, which gives you a nice estimate of that. But in terms of a prediction, I should mention that this gives you the value of the coefficient. And this is in scientific notation. It is basically, and I'll have to look at that. The coefficient in front of horsepower is 123.6562. The coefficient in front of year is 915.8551. And then cylinders is a minus 819.3702. So, and let me just make sure I have this right. I always get confused over okay. Okay, so that is, let me just see. I'm trying to see. No, it can't be. Help me out here. Yeah, so basically scientific notation is e to the plus 06 basically says, take 1.00 e to the 06 would be 1 million. That's what I was kind of looking for. So this basically says take -1, and I guess it's telling us to move the decimal place over 6 places. And so this coefficient, just see, is 1.836, and then we do 1, 2, 3, 4, 5, 6. Okay, so that says basically, if I have this correct, what it's saying is the predictive model is going to be basically starting off with a constant of a negative $1,836,000. What you want to do is take your number of horsepowers times 123.6562 plus take the year of the vehicle times 915.8551 times the number of cylinders times a negative 819.3702. Do that calculation, and that is your estimated price. And you can do other things like how to print MSE and stats model. Yeah. And Dennis wanted to know if you have a high uncertainty and predictability is unlikely, would it then be best to just suggest other areas of studies to that could possibly expand your model? And I think what you're saying is, oh, here we go. I think this is what you can use. So, let's see. Wonder if I can do this. This. I'll have to play around with this. I think yeah, so in answer to Dennis's question, yeah. So sometimes you can only go so far with your model, and you conclude, maybe I'm not getting the results that I need to get with regression. And that's when you might try a different model. You may say, let me try a neural network. Let me try a decision tree. And this is where, yeah, you end up going out and saying, well, yeah, let me try some of the other models that are out there. And this is why people start playing around with things like decision trees and random forests and, support vector machines and neural networks. People start playing around different models just to say, hey, is there a way that I can find a more sophisticated machine learning model that's able to work? Maybe the problem is there are other attributes that you need to be capturing. This is why it can be kind of interesting, I'm just curious, when you go to sites like Edmunds, how their models are working. Though I suspect, when you put in your vehicle, I bet they have a whole lot of information about that vehicle, like the horsepower, the cylinders, and everything that automatically gets inputted into their algorithms. So if it helps is, and Dennis, in terms of this course, I also should mention, suppose you do a really good job and you just beat the heck out of regression models, and your conclusion is, hey, the best model I can get is this model. And that is fine. There's nothing that says that you have to come up with a really great model. What I'm really interested in is more, the models that you tried, did you really beat the heck out of them? And if that's the case, that's what I'm, and the fact that you recognize, hey, I tried a bunch of different models of different variables, tried, looking at different relationships, looked at different things I could do. So far, this is, the best I can come up with. But if I had more time, here are some additional things that I think I would try. That is just fine. So Dennis, maybe that would help. Let me put it this way. Your job is not to find the perfect model, because sometimes the perfect model does not exist. You're just really showing me that, hey, I put in some decent work into this project. And I really, started early and, Googled, what I could do with stats model and, how many things I could model and try to capture. And based on what I've learned from stats model, this was the best model in my estimation that I could come up with. Here's what the model looks like. And, if you put the values in, here's how I would make a prediction. And I'll look up how to print out the mean squared error, since that's a good guesstimate of essentially what is the, you make a prediction, but what's sort of the prediction range? You see that all the time. In the election, they would say, 38% are for Harris, plus or minus 3%, meaning saying that, they're predicting 38%, but the right proportion in the population that they're looking at that would vote for Harris, could be as low as 35% or as high as 41%. So that plus or minus 3% is basically, based on the confidence in their model. Here's their best guess, but the plus or minus 3% gives you, well, we could be as off, by this on the low end and off by this much on the high end. Okay. And as always, we are out of time. We will pick up next week. One little change to the schedule. Dr. Dactus would like to start multimedia analysis the week after. So what we'll do is we'll wrap up what we're talking about. I'll maybe say a few words about R on Tuesday, and then we'll go into text mining. So I just took week 8 and moved it after week 3. But Dr. Dactus is looking forward, in about 10 days from now, talking to you about multimedia analytics. Okay, so that's all I've got today, and we're out of time. So have a good weekend.